This example is going to illustrate what you do with repeated linear factors. All right, so you see we've got a rational function here. The denominator is already factored. We have x plus 1, which is a linear factor, and then we have x plus 3 squared, so that is a repeated linear factor. The way this is going to break up, it's going to be something over x plus 1 plus something over x plus 3 plus something over x plus 3 squared. If you have a repeated linear factor, that factor is going to give rise to two pieces of the decomposition. If it was the third power, we'd have three pieces. We'd have a third piece with a third power in here. Okay. Now, to figure out what the numerators are, we can use the cover-up method for a couple of them. Okay. To figure out what goes above the x plus 1, we can cover up the x plus 1. We can plug in x equals negative 1, just like we've been doing. If I plug in x equals negative 1, 2 times negative 1 would be negative 2 plus 1 is negative 1, so this would be negative 1. On the bottom here we'd have 2 squared, which is 4. So this would be negative 1 over 4. Okay. We can figure out what goes above the x plus 3 squared because we can cover up the x plus 3 squared and we can plug in x equals negative 3. Okay, if I plug in x equals negative 3, I'd have on top, I'd have negative 6 plus 1, that's negative 5. On the bottom, I would have negative 2. Negative 5 over negative 2 is positive 5 halves. Oops. Okay. Unfortunately, I cannot do the cover-up method to figure out what goes above the x plus 3 because I can't just cover up one of the x plus 3's and plug in negative 3 because I'd be dividing by 0. So you cannot use the cover-up method to figure out this one here, so I'm going to use the books method and just call it a temporarily. Okay. Now we're going to use the books method to solve for a. What we're going to do is we're going to multiply both sides by that common denominator of x plus 1 times x plus 3 squared. The left-hand side would just be 2x plus 1. With the right-hand side, you're going to multiply all three of these fractions by that common denominator. Each time something different is going to cancel. When I multiply the first fraction times the denominator, the x plus 1's cancel. I'd be left with negative 1/4 x plus 3 squared. When I multiply the second fraction times that common denominator, one of the x plus 3's will cancel. I'll have a times x plus 1 over x plus 3. Sorry, a times x plus 1 times x plus 3. When I multiply the third fraction times that common denominator, the x plus 3 squareds cancel. I'm just going to get 5 halves times x plus 1. Okay. Now, since there's only one unknown to solve for, a, probably the easiest thing to do here is to just plug in an x value. And we want to avoid negative 1 and negative 3 because that would wipe out the a term, but literally we could plug in anything else for x and it would give us the correct a value. So let's try to plug in something simple. Let's maybe plug in x equals 0. If I plugged in x equals 0, I'd get 1 on the left. I'd get negative 1/4 times 9. I'd get a times 1 times 3, so that's 3. And I'd get 5 halves times 1, which is 5 halves. Okay. One thing you could do to get rid of those fractions, I could multiply both sides by 4. if I multiply both sides by 4, I'd have 4 equals negative 9 plus 12a plus 10. So 4 is 12a plus 1. If I subtract 1 from both sides, 3 is 12a. So a is 3 over 12, otherwise known as 1/4. Okay, so a little bit more work to try to figure out what the numerator is in that case, but we found it. So the integral of this rational function, I can split up as 3 different integrals. I can split it up as negative 1/4 integral of 1 over x plus 1 dx, plus 1/4 integral of 1 over x plus 3 dx, that was the a that I just found, and then plus 5/2 integral of, and then this last one here, I'm actually going to write it slightly differently. I'm going to write it as x plus 3 to the negative 2 power. Okay, and you got to be a little careful because when you're doing these partial fraction problems, you get a lot of natural logs for your answers. In fact, the first 2 integrals are natural logs, right? The first one's going to be natural log of x plus 1. The next one is going to be a natural log of x plus 3. Okay, both of those, technically I did u substitutions there. But the last one is not a natural log. Okay, the last one, we have to use the good old power rule where you increase the power by 1 and divide by that number. If I increase the power by 1 here, the new power would be negative 1, and then divided by negative 1 would give us actually minus 5/2 x minus 3 to the negative 1 power. Okay. Again, technically, I'm doing a u substitution there. U equals x plus 3, but then du is just equal to dx. Yeah, but I'm going to put a box so that this is my final answer here. It is very important to realize that this last term here is not a natural log. Okay, you get really used to getting natural logs for your answers when you're doing partial fractions. You do get a lot of them, but you do have to be careful because if you're integrating a factor where the denominator is squared, this integral is not going to be a natural log. What you want to do is you want to rewrite it as the negative 2 power and then integrate it using the power rule.